Okay, now again welcome to electrical machine electrical machine lecture. Today we are discussing transformer. In last lecture we discussed some construction introduction of transformer, and in introduction of transformer, what is the need of transformer in power system, what is the importance of transformer in power system. Second is the construction. So just we will take the review. The construction, it is comprises of magnetic material core, and this core is laminated to reduce the eddy current loss and hysteresis loss. No doubt we will see in detail what is the eddy current and hysteresis loss in transformer. But core is not a solid one, it is laminated. There are number of strips are there, and after they are sticks with the help of laminated varnish are there, and it is bagged into the ovens for drying. That laminations are there. Okay, so these are the laminated core, and over this laminated core the winding is carried out. There are two windings, so it is called as a two winding transformer. It is a two winding transformer. Two winding transformer. Okay, so this is a two type of construction. One is the core type construction, where the winding is placed, one winding placed on one limb and second winding is placed on the second limb. And whereas in the shell type transformer, the both primary winding and secondary winding, or you can call as a winding 1 and 2, both are placed on the central limb. So the advantage is that in case of shell type transformer, the leakage flux is smaller. Okay, so but for our understanding purpose and for working operation of transformer, we will consider as a core type transformer, and one winding plays on one core and second winding is placed on the second core of the transformer, that is a limb on the transformers. Okay, so first of all, we will see the what is the working operation. The working operation of the two winding transformer is according to the Faraday's law of electromagnetic induction. So it is a statically EMF induced. So it is a static EMF induced in the transformer. So transformer is a static device which transfer the power from one circuit level, one circuit to the other circuit without changing the frequency. The frequency of the transformer with the frequency of transferred voltage is remain same. So if it is a 50 hertz, so you will get the 50 hertz in the secondary winding of the transformer. If it is a 60 hertz, so you will get the 60 hertz transformer only. The voltage level can be changed. The power as again will remain same. Okay. So in the last, we found that if two windings are placed side by side, and if it is connected, one winding is connected with variable resistance and it is connected with the DC link or DC power. So it produces the magnetic flux. That magnetic flux linked with the second coil, and it induces, or it will give some sort of the deflection in the galvanometer or voltmeter it is connected. So coil A and coil B. Now the change in voltage or voltmeter is going to observe only when there is a change in magnetic flux. If the flux become constant, at constant current, the voltage induced it becomes zero. It means that the EMF induced E is equal to minus N d phi by dt, where d phi by dt is nothing but the rate of change of flux are there. So as long as there is a change in magnetic flux, there is a change in EMF is going to induce in the second coil. Because both coil are stationary, the cutting of magnetic flux is will not be like a DC motors and say DC generator and all these things. It is a statically EMF induced. So now what we will do, we will replace this DC source by a single phase AC source. If you connect a single phase AC source to the winding, so definitely the flux is alternating, voltage is alternating, the flux also alternating, and this alternating magnetic flux linked with the second coil and it induces EMF. So transformer work on AC supply only. So here the AC supply is connected. This is the winding which is connected with the source is called as a primary winding, and the winding which is connected to the load, if there's a load is there, here the load is not shown, just for the understanding purpose. So if the load is connected to this winding, it is called as a secondary winding. So we can call as a primary winding, and this is secondary winding, secondary winding. Okay. Now, this winding may be called as depend upon the voltage. So either suppose that winding which is connected with the source is a HV winding, high voltage side, and the load is connected to the LV side. So it is called as a LV winding and HV winding, and vice versa. Suppose it is connected to the low voltage, so it is a low voltage winding and high voltage winding. So the winding, it may be, we will give the terminology as a primary winding and secondary winding. So by default, primary winding, the winding which is connected with the source, and the secondary winding which is connected to the load. And the second terminology we can use as a HV winding and LV winding, which is depend upon the voltage level and the number of turns in the primary winding and secondary winding. More the number of turns, more will be the voltage. That is called as a HV winding, and less number of turns is the low voltage winding. How it is going to occur? Okay, we will see one by one how the voltage is going to change with the respect to the number of turns are there. Okay, now first of all, we will see some ideal transformer, two winding ideal transformer, and from this ideal transformer we will consider one by one and try to understand the working operation as well as the performance of a transformer with the help of some these characteristics are there. So first point for the ideal transformer. This is assumption for understanding purpose. Ideal two winding. Ideal two winding transformer. Ideal two winding transformer means we will consider, we will assume some date, and from this assumption we try to understand the operation of transformer. First, that the winding resistance is neglected. The winding resistance is neglected. No doubt, when there is a winding, primary winding or secondary winding, which is made up of copper, even a best grade copper if you are using, but it has some resistance that is depend upon the length, cross-sectional area of the conductors and so on. Okay, so this is the this one. Second is that all flux set up by primary winding links with secondary winding. Okay, so it is quite it is our assumption is that whatever the flux created by the primary winding or the winding which is connected with the source, which link with the secondary windings, no flux is going to make some short circuited path. So no doubt in practical cases the flux get short circuited path on the primary as well as secondary. So there is some leakage flux are there. But for our first assumptions, for our understanding purpose, we assume that there is no winding resistance. Basically, it is not true. The winding has some resistance. Second, all the flux set up by the primary winding links with the secondary winding. Then third point is that the core losses are negligible. The core losses are negligible. Again, it is not realistic that the core have some they have no losses. No doubt, the core having some losses is the iron losses and eddy current loss. But for our understanding purpose, we are making some assumptions. And fourth point is that the core has constant permeability. The core has constant permeability. Permeability. Okay, so it means that as we increase the current, the flux is go on increasing. The transformer is designed at linear part of the BH curve. Okay, so just we will take before going to the next point. What is the it meaning? Say this is the EM, it is the magnetic flux phi, and it is the current I, or it is maximum flux density or M, and this is the value of H. So BH curve is like that one. There is some saturation part is there. Okay, this is the saturation part, but the transformer is designed on the linear part. So this is the linear part of BH curve, magnetic material, and this is the saturation. So transformer is designed on the linear part, so it will give the constant value of say permeability over this one. Okay. So one more thing before going to detail in the transformer, in the construction of the transformer, the transformer which we'll use as a practical transformer. If suppose if you take the top view of a limb, this may be like that. This may be this is the cross-sectional area of magnetic material. Okay, it is a laminated one. But in practical cases, what you will do, if you use the bobbin or winding over this one, you have to make some particular round shape of the bobbin, and over which we will place the number of turns, or it is called as a winding. It may be HV winding or it may be LV winding. So if such type of construction are used for the limb or for the core, no doubt the mean diameter of the winding is gone increasing. When the diameter get increases, no doubt the length of the conductor also increases, which will increase the resistance and the voltage drop across this one. So instead of this one, we are using the crucible construction. What is the crucible construction? Instead of using all laminated core, all cores or all strips of the same size, we will make some different size. For example, here one section of this side, second section is smaller, somewhat smaller. Again, there is some again smallers are there. Okay, so by this way, I will just draw some a bigger figure. Say this is the first step or size of the cores are there. Okay, so this is the laminated core. Second one will be somewhat smaller. Then again, the third steps is smaller. Again, next is small. It is depend upon the best compromise between the cost and performance of the transformer. Okay, so here it is called as a crucible core. Now, what is the advantage here? The mean diameter of the circle get increases, whereas the net iron area, AI, net iron area available, net iron area will remain same. Here net iron area will remain same. Only the size of the diameter, mean diameter of the winding get reduces, which will decrease the length of conductor. Second, because of this one, we will find some air gap. We will find some air gap here, we will air gap here, and here we are able to reduce the air gap over the windings. So there are two advantages. One is that it reduces the mean length, mean diameter of the winding, which will reduces the total length of the conductor required by the primary winding and secondary winding. The advantage of this one is reduce the resistance and losses in the transformer. And second is that it reduces the air gap. So this is the way by which we can construct the crucible construction of the transformer. So all practical transformer bigger size transformer has a core in the shape of crucible form. Okay, whereas for the small transformer, it is just like a rectangular shape of the limb, or it may be a square shape of the limb is there. Okay, now we will consider the working operation of transformer, and from this working operation, we will consider our assumptions. So first assumption is that the winding, there is no winding resistance. Second assumption is that the whatever the flux created by the primary windings links with the secondary windings. And the third assumption is that the core losses in the transformer is zero. And fourth assumption is that the transformer has a constant permeability, or it can be said that the transformer has the transformer is designed on the linear part of the circuit. Okay, now let we have applied the voltage V1. Here it is the voltage V1 is applied to the primary winding, and it is equal to the V is equal to V maximum into sine omega t, and therefore the flux setup, the flux phi, is also with the same shape and characteristic phi maximum into sine omega t. So this is the, say, phi, and this is your times omega t. So somewhere the flux become maximum, and this one. So this is the maximum flux is there. This is phi maximum. Okay, and it will follow the same wave shape is there. Okay. So the when the voltage is applied to this one, it develop a small current is going to flow in the winding, and that winding current is IP. It is the exciting current, the current needed to set up the magnetic flux in the core, or it is called as a working flux system. Okay, so as per the Faraday's law of electromagnetic induction, the flux which is created by the primary winding, it linked with the secondary winding. As the flux is changing with respect to time, so it induces EMF in the windings. So EMF induce E1 induce in the primary, in the, let the number of turns in the primary winding is N1, and the number of turns on the secondary winding is N2. So therefore E1 is equal to minus N1 d phi by dt. Okay, so number of turns, the flux which is linking with the primary winding, and it is equal to minus N1 d phi by dt is nothing but phi maximum sine omega t. So derivative of this one is, or we can write one equation, d upon dt phi maximum sine omega t, where minus N1 omega phi maximum into cos omega t. Okay, so this is the cos omega t. Now we can write this equation as we remove this one N1 minus N1, so it is the N1 omega phi maximum into sine omega t minus pi by 2. Okay, so this is the equation EMF induced in this one. If the maximum value, let we consider that E maximum 1 is the maximum value, which is equal to what is that value? It is N1 omega phi maximum is the value for that one. So therefore E1 is equal to, we can write as E maximum N2 sine omega t minus pi by 2. So this is the EMF induced in the primary winding. E1 is equal to E maximum to. Now RMS value, we'll put the RMS value. RMS value. RMS value we can write as E1 is equal to say maximum value divided by root 2, and which is equal to if you put this value, so n1 as it is omega, it is twice pi f. Okay, n1 n1 we have written, it is a phi maximum, okay, divided by root. So it is equal to this root 2 2, so it is a root 2. Just arranging this equation, pi f n1 phi maximum. So this is the value, it is the RMS value. So we can write the equation as E1 EMF induced in the primary winding is root 2 phi root 2 pi f phi maximum. Okay, so say this equation number 1. How it is equation? Just we'll again review this one. We have taken the supply voltage is alternating, V is equal to V maximum sine omega t. Therefore, the flux also phi is equal to phi maximum sine omega t. EMF induced in the primary winding, EMF induced here, induced in the primary winding is E1 is equal to minus n d phi by dt. So if you put the value of d phi by dt here, rate of change of flux, derivative of the flux, minus n omega phi maximum cos of omega t. So just rearranging or putting this, removing this minus sign, E1 is equal to n1 omega phi maximum sine omega t minus pi by 2. Now this value is nothing but the maximum value. Okay, so we have replaced that maximum value by written as a E maximum sine omega t. Now E1, this is the maximum value. So in terms of RMS value, so RMS value for the sinusoidal waveform, it's divided by root 2. So we found the equation in EMF induced in the primary winding is E1 is equal to root 2 pi f phi maximum. Okay. Now, when the same flux is going to, we can write as a V1, which is so again we'll draw this equation, this circuit as so it produces some flux. Okay, and EMF induced number of turns is N1, number of turns is N2. Already we have assumed number of turns in primary winding and number of turns in the secondary winding. So it induces EMF is E1 and the voltage is V1 and EMF induced is minus E1 because the voltage induces in the primary winding opposite to the voltage source. Okay, so this is the representation, the EMF induced in this form. Okay. Now, second point, it's very important to consider that from this equation that the EMF induced is lagging by 90 degrees. Okay. Now, from this equation, we consider that we say that the EMF induced in the primary winding is lagging with respect to the flux. So now say this is the setup voltage flux setup by here we have considered that there is no eddy current and hysteresis loss. So the current is IE, exciting current, which we have considered here because of flow of this one. Now this is the flux phi, and this is the voltage applied voltage is V1. It induces EMF which is lagging by 90 degrees. So your EMF induced is E1, which is lagging by 90 degrees. It is always anti-clockwise direction. So EMF induced in the primary winding, which is lagging by 90 degrees with respect to the flux. Okay. Now, similarly, we can say that the EMF induced in a secondary winding, EMF induced in a secondary winding, which is equal to E2 is equal to minus N2 d phi by dt. The flux is same. The flux is a common quantity in transformer. See here the flux. Here, see the flux. It is common for primary winding and secondary winding. So d phi by dt the same. D phi by dt. If you derive with respect to time, with respect to t over this one, so we'll get finally we'll write this equation as minus n2 omega phi maximum n2 cos of omega t. So which is written as n2 omega phi maximum into sine omega t minus pi by 2. So here again, it is a sine omega t minus pi by 2. So we can represent E1 and E2 is going to induce, which is lagging by 90 degrees. Okay. So so again, we'll have an equation and diagram. So this is our winding is connected with the source is V1. Secondary winding we have kept open. Number of turns in the primary winding is N1 and here N2. Okay, EMF induced is E1, which is opposite to the supply voltage. EMF induced is E2 in the secondary winding, whereas the flux is constant, whereas the flux is common in the primary winding as well as in secondary winding. So flux is common. So it's say vector diagram. The current is in phase. It is a I2, IE. The current is here is IE, exciting current, which is responsible to produce the required magnetic flux in the core. And EMF induced in the primary winding and secondary winding, it is lagging by 90 degree with respect to phi, and the flux here the voltage is V1. Voltage is V1. So our EMF induced in the primary winding E1 is equal to we have written it is twice pi under root 2 pi f n1 n1 into phi maximum. It's the RMS value. Okay, and the equation can be into phi maximum sine omega t. Okay, so it is the sine omega t minus pi by 2. Okay, and again we can write equation E2 is equal to under root 2 pi f n2 phi maximum sine omega t minus pi by 2. Okay, so this is the RMS value. EMF is the RMS. Sorry, this is, if you don't write, it's better. So we are writing only the RMS value over this one, only the magnitude. So we have these two equations, RMS values of EMF induced in primary winding and secondary winding. So under such condition, if you take the equation as E1 upon E2, which is equal to root 2 pi f n1 phi maximum and divided by root 2 pi f n2 phi maximum. So it is quite clear that the value of E1 upon E2 is equal to N1 upon N2, and this is common. This is common. Whereas, so or the value of the voltages is directly proportional to the number of turns. More the number of turns, more will be the this one. Or we can write as a equation. Say this is equation number 3. And equation number 4 we can write as E1 upon N1 or E2 upon N2 is equal to root 2 pi f phi maximum. So this is our very important equation for the transformer, and a basic equation. The voltage in the primary winding and voltage in the secondary winding depend upon the number of turns. So N1, more the N1, if your N1 is greater than N2, the transformer is called as a step down transformer, because the voltage getting to the load is smaller than the supply voltage. Okay, so it is a step down. If your N2 is greater than N1, so it is a step up. The voltage is going to increase. So it is a step up transformer. And whereas the voltage per turns, it means that voltage, this one, voltage per turn is same for primary winding and secondary winding. What it means, see here, this equation, RMS value of EMF induced in the primary winding is root 2 pi f n1 phi maximum, and for the secondary winding it is E2 is equal to root 2 pi f n2 phi maximum. If you take the ratio, we found that the EMF induced in any winding, it is depend upon the number of turns. More the number of turns, more with the voltage. And from this one, the transformer is going to decide either it is a step up transformer or it is a step down transformer. Second conclusion is that voltage per turns. See, this is E1 is voltage, N1 is turns. So voltage per turns. Voltage per turn for primary winding, voltage per turns for secondary winding is equal to the root 2 pi f phi maximum. Means it value is same. For example, the voltage per turns is 2 volt per turns, 2 volt per turns for the primary winding. Same will be the 2 volt per turns for the secondary winding. So we'll take the example to understand. Let the number of turns is 100 and N2 is equal to 200. The primary voltage is V1 is equal to say 200 volt. So what is the voltage per turns? V1 upon N1. This is N1. It is 200 divided by 100 equal to 2. So 2 volt per turn. So what would be the voltage induced in the secondary winding? So V2 is equal to N2 multiplied by voltage per turns. Voltage per turns is 2. Okay. So it is a 400. So see here, if more the voltage, number of turns is more, voltage will be more. So here N1 or V1 upon V2 is equal to N1 upon N2. Means more the number of turns, more be the EMF induced in the secondary winding, and less the number of turns, less will be the EMF induced in the secondary winding. And voltage per turns means V1 upon N1 and V2 upon N2 is equal to the, it will remain constant, or constant means it will remain same for particular transformer. One transformer which having the voltage per turns is 2 volt. So primary winding and secondary winding will have a same over this one. Now, for that purpose, we say that the phasor diagram under such condition, under no load condition, so here this is the flux phi. Okay, voltage applied is V1. It will produce some, it will require to flow, there is some exciting current, IE. We have drawn this exciting current exactly 90 degree with respect to the supply voltage, because we have considered that there is no eddy current and hysteresis loss, but it will make some angle with respect to phi. Okay, we will see one by one. So it will induces EMF which is lagging by 90 degree. Lagging, we refer phasor diagram always anti-clockwise direction. So the flux phi is there. It is the EMF induced E1. EMF induced in E2, it is lagging by 90 degree. It is lagging by 90 degree. So this is the says for the simply for a transformer. So what is the points which we have considered today? Point one is that ideal transformer, two winding ideal transformer. In the construction of the transformer, there are two types. One is the core type, second is the shell type. It having only the two windings, so it is called as a two winding single phase transformer. Second point is that the core is not a rectangular one, it is a crucible core. There is a stepped core is there to reduce the mean diameter of winding. And second is that to reduce the mean diameter, which reduces the length of the conductor, length of the winding wire, which reduces the resistance and voltage drop across the voltage drop across the primary and secondary winding. In case of shell type transformer, suppose this is the top view of shell type transformer, is that this is the central limb is there, okay, and this is the side limbs are there. This is the top view of transformer. The winding, primary winding and secondary winding both are placed over the center limb. So this is the first winding, and this is the layer of first winding. Okay, and see this is the, say for example, this is the layer of second winding. So the second winding, which is away from the core, is a HV winding, low high voltage winding. This is your HV winding. Whereas the winding which is near to the core is the high voltage winding. Sorry, low voltage winding. What is the reason? Because the core at zero potential. Okay, the core has a zero potential. Therefore, the insulation required for zero potential core and LV winding will be thinner, small in thickness. Uh, and if you place the HV winding next to the core, the insulation required will be more, and which will increase the length of the mean diameter of the winding, which increases the length of the conductor. So in practice, always first winding is the LV winding, and next winding will be the HV winding for the shell type single phase transformer. Okay. Now we have made some assumption. Assumption number one is that winding has no resistance, but in practice there is a winding resistance. So we will consider the resistance losses in the transformer. Second, core has uh, no type of eddy current and hysteresis loss, but in practice, all type of core are having some losses. Just our assumption for understanding purpose. Third is that all whatever the flux created by the primary windings link with the secondary winding, and from this one we come to the equation. Equation is that the EMF induced in the primary winding and secondary winding lagging with respect to the flux, and whose values is equal to root 2 pi F N1 phi maximum, and the ratio of number of turns to the voltage to the number of turns is the turns ratio. Turns voltage per turns is same for primary winding and secondary winding. The voltage level of primary and secondary winding is depend upon the number of turns. More the number of turns, more will be the voltage across the winding. So today we will stop here, and from the next time we will give the transformer on load condition and under its phasor diagram.